All right, everyone. So welcome back as we continue our discussion on derivatives. Before we do that, I want to remind you that tomorrow what I'm going to do is do a video on a computer algebra package called Sage. There are instructions in WILE courses in how to download it and install it on your own computer. If you have any trouble getting that to run, please send me an email and we'll try and get it all taken care of. Also, remember that your second homework is due on Thursday, and on Friday we will have our first test. Okay, so last time we saw this idea of a derivative and a tangent line. So I don't think we need to go over that again, but we're going to keep building on this. And particularly what we saw at the end was the derivative function. Right, so this f prime of x is given by the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Um, so again, our rise over run for very small runs, effectively. And if f prime exists at every point, we say that f is differentiable. And if f is differentiable on some open interval, we say that f is differentiable on that interval. Okay, so we want to go and do some more examples for finding the derivative function. So the first one that we're going to start with is the function f of x equals 7. So for every number you pick, f of your favorite number is 7. Right, so we want to find the derivative. Well, so we have the limit as h goes to 0 of f of x plus h minus f of x all divided by h. Well, f of x plus h is 7, and f of x is also 7. So that tells us that our numerator in this limit is going to be 0. Um, Now, you might want to object and say, well, the numerator is 0, that's great, but the denominator is also going to 0. And that is true. But for, remember that when we take our limit, h is never actually itself 0. It's always some non-zero number in this. It's going to be some non-zero number every time. So our numerator is going to be 0, and it's going to be divided into something that is non-zero. Regardless of how small that non-zero is, the um, the limit value is always 0. So um, for every h, the limit is always 0, regardless of what you pick. And that's going to tell us that we're looking at the limit as h goes to 0, we wind up with just 0. And this makes sense because if we're taking the derivative function to give us a rise over run, if our function is a fixed constant like 7, the rise is always 0. So we would expect our derivative to be 0 everywhere. So that's nice. Okay, for our second one, well, we just did a constant. The next nicest thing to look at is going to be a linear term. So just g of x equals x. In that case, g prime is still given by the limit as h goes to 0 of g of x plus h minus g of x all over h. From our definition, that's going to be the limit as h goes to 0 of x plus h minus x all over h. The x's will cancel each other out, and we just get left with h over h, which is 1. And again, remember that when we're doing these, um, when we go through our steps of simplification, if you ever in the numerator have a term kicking around that does not have an h in it, that tells you that you've done something wrong. So either you've flipped a sign, or maybe you've added or multiplied or something incorrectly. Just go back, check your work, make sure that you've got everything right. Because what we want is everything in the numerator that doesn't get canceled out to have an h in it. Because if we don't, we're in a lot of trouble. Okay, so our next example. So we did g of x equals x. Now let's do g of x equals x squared. Well, so we take our limit as h goes to 0 of g of x plus h minus g of x all over h. And we get the limit as h goes to 0 of x plus h all squared minus x squared all divided by h. When we expand out the x plus h all squared, we get an x squared plus 2xh plus h squared. the x squareds nicely cancel, and everything that remains in the numerator has an h in it. So then we can factor the h out in front, and we get left with the limit as h goes to 0 of 2x plus h. And again, this we can treat as a polynomial in h, so we can just evaluate 2x plus h at h equals 0, and we get 2x. Okay, for our, what is this, fourth example, let's take f of x to be the square root of x, and because the square root function is not defined for negative numbers, we'll assume that x is at least 0. So we take f prime of x, as is typical, to be f of x plus h minus f of x all over h, and we take the limit of that as h goes to 0. So we get the limit as h goes to 0 of the square root of x plus h minus the square root of x all over h. And what we have here is we have square roots that are kind of a hassle, so our numerator is clearly going to 0, our denominator is also clearly going to 0. But what we'd like to do is get the square roots to, I guess, work in our favor. So what we'll do is, as has been kind of typical whenever we've had square roots that have been a hassle, we'll pull out the conjugate. So we'll multiply both numerator and denominator by square root of x plus h plus square root of x. And then that tells us that our numerator is now going to be a difference of squares, which will give us x plus h minus x, and conveniently those two x's will cancel each other away, leaving us with just h in the numerator, which will then nicely cancel with the h that was sitting in the denominator. So we get left with the limit as h goes to 0 of 1 over the square root of x plus h plus the square root of x. Okay, so now what we'd like to do is go and pull out our quotient rule. So go and pull the limit down to the denominator. But the one thing that we need to do here is we just need to make sure that the denominator is not going to be 0. So we're going to kind of split this into two cases. So first, if x is 0, so we were trying to find the derivative for square root of x at x equals 0, we would just be left with 1 over the square root of h as h goes to 0. Well, 1 over the square root of h as h goes to 0, using the rules that we had um, for dealing with limits going to infinity, that limit would be infinity, which will tell us that the derivative for square root of x does not exist at x equals 0, because the limit would go off to infinity, and those limits do not exist. So because the derivative limit does not exist at x equals 0, the derivative doesn't exist at x equals 0. Okay, so now what we'll do is we'll say we have x values that are positive, because again, we're only assuming that we're dealing with non-negative x values. So if you have a positive x value, then our denominator won't be going to 0 as h goes to 0, so that's good. Then we can use our quotient rule to say we have 1 over the limit as h goes to 0 of square root of x plus h plus square root of x. Then we can use our sum followed by the power rule to go and switch the order of the square root and the limit, because again the x plus h will be something positive as h goes to 0, because we're assuming x is a positive in this case. So we get, as h goes to 0, the limit, the limit as h goes to 0 of x plus h is just going to be x. So what we wind up with is 1 over 2 square root of x. But that only works if x is positive. Again, if x is 0, the function exists, the function is perfectly well defined, but the derivative does not exist. Okay, so that's one interesting example where the function is defined, but the derivative does not exist. Well, how about this next one? So, absolute value of x. So we'll take our definition for derivative as usual. We'll take g prime to be the limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x, all divided by h. And in this case, for this one, kind of like the square root function, we're going to break this up into a couple of cases. So the first one is we're going to assume x is a positive number. Well, if x is a positive number, as h goes to 0, the absolute, let's see, as h goes to 0, x plus h is positive because x is positive. So absolute value of x plus h is just x plus h, using the definition of the absolute value function that we had from a couple of videos ago. I forget offhand. And the absolute value of x is just x because x is positive. Okay, so the x and the minus x cancel each other out. We get left with the limit as h goes to 0 of h over h, which is 1. So if x is a positive number, the derivative of the absolute value function is 1. Okay, well, case 2, x is a negative number. In this case, x plus h will be something negative. So the absolute value of x plus h, we'll write it as minus the quantity x plus h. And also, because x is negative, we'll write the absolute value of x as minus x. So we'll go and just pull some minus signs through, and we'll get the limit as h goes to 0 of minus x minus h plus x, all divided by h. Well, now we get that the limit as h goes to 0 of this expression is going to be minus h over h, or minus 1. Okay, so if you have a negative number, the derivative for absolute value of x at your favorite negative number is negative 1. Okay, so we've covered the positives and the negatives. The only thing left to do is look at x equals 0. So at x equals 0, we're looking at the limit as h goes to 0 of absolute value of h over h. So we'll break this into looking at a left and a right side limit for h equals 0. And if we take the right limit as h goes to 0 of absolute value of h over h, because h is positive, we get just the right limit as h goes to 0 of h over h, which is 1. But if we take the left limit, h is now negative, so absolute value of h is minus h. We get the limit as h goes to 0 from the left of minus h over h, which is minus 1. So the left and the right limits don't agree, and that tells us that the derivative for absolute value does not exist at x equals 0. Okay. All right, so if we were to write out the derivative for the absolute value function, we'd just have 1 for positives minus 1 for negatives does not exist for x equals 0. And the reason for this is that if you plotted out the absolute value function, what you would see is that it looks kind of like a V, where the point is occurring at 0. And whenever you have a function that has a point, very much like the absolute value function, your derivative won't exist there, because you could think about it as you're making a very sharp turn. In this case, you're immediately flipping from minus 1 to 1. So when you have this discontinuity in the derivative function, your derivative will not exist at that point. So in this case, this corner, formally the term is a cusp, but we can just refer to it as a corner, tells us that the derivative won't exist at this point. Okay, so we can also go and look at a function that we've looked at a few times in various contexts. So minus x times x minus 3 in blue, and then its derivative function, which we found last time, minus 2x plus 3, plotted in red. Right, so one of the interesting points is that when the red line hits 0, the curve is flat. So the tangent line is flat at this point. And then everywhere, well, okay, so then we can look at one function that we've seen a couple of times in various contexts. So f of x is minus x times x minus 3, which is plotted in blue, and the derivative function, which we found last time, minus 2x plus 3, is plotted in red. So one interesting thing that we can see from this plot is that when the red line is at 0, the blue curve is flat. So the tangent line there is flat. And, that's not really a coincidence. Right, and then what we could do is we could plot a couple of tangent lines on minus x, x minus 3, so tangent lines at a half, 3/2, and 5/2. What we see here is that the derivative at 1/2 is positive, the derivative at 3/2 is 0, the derivative at 5/2 is negative. So now we'll go and find some explicit equations for the tangent lines at 1/2 and also 3/2. So we know that our derivative function is minus 2x plus 3, and by going and putting 1/2 into this expression, we could find that f prime at 1/2 is 2, and also f of 1/2 is 5/4. So we get that our tangent line equation is going to be y equals f prime of a times x minus a plus f of a. And going and putting in the things that we've just found, we get that the tangent line is 2x plus a quarter, right? And that makes sense because we said that the derivative is positive at 1/2. So this works out quite nicely. Okay, for the other one, we said that at 3/2, the tangent line is going to be flat there. And the reason for that is that the derivative is 0 at that point, right? And that's something else that we just mentioned. So when we find the tangent line at 3/2, we're going to get that because f prime is 0, we just get that y is going to be equal to f of a equals 3/2 in this case, which is 9/4. So the tangent line to f of x at 3/2 is just the line y equals 9/4. Okay, and then something else that we could look at, which we'll come back to in about a week and a half or so. What we have here is a place where the function has 3 places. This blue curve, this kind of blue W, has 3 places where the tangent line is flat, and that nicely corresponds with where the derivative function hits the x-axis. And what we'll see is that these places are kind of important. Okay, so one result that's kind of useful is if f of x is differentiable at a, then f also has to be continuous at a. Now, be careful because this does not tell us anything about the reverse direction. This does not say that if f is continuous at a, then it is differentiable. And in fact, we have an example where that's false. And so we just saw that if you take the absolute value function at x equals 0, the function is definitely continuous at x equals 0, but it's not differentiable there because the derivative doesn't exist at x equals 0. Right? So again, think about it in terms of what I have written here. So if you're in Disney World, then you're in Florida. But just because you're in Florida, it does not mean that you're in Disney World. You could be in Miami, you could be in Tampa, you could be in Jacksonville, you could be in Tallahassee, you could be somewhere else entirely. So that's just one thing to keep in mind with a result like this. Okay, so then we'll wrap this discussion up with one more example. So we're going to take the position of a stone that gets thrown into the air to be given by minus 16t squared plus 96t plus 40. We want to find our average velocity from t equals 1 to 4, our instantaneous velocity at t equals 5, and then find the maximum height that this stone reaches on its journey. Okay, so the first thing that we can do for average velocity. Remember, this is just simple rise over run. So we'll take p of 4, subtract off p of 1, and then divide by 4 minus 1. And then when we expand everything out and we simplify, what we see is that our average velocity is going to be 16. And if we want to be really precise on this one, we should also really include units. So let's say that our stone is being measured, that our units are feet, and our time unit is seconds. So we'll have that our average velocity over the time interval 1 to 4 is 16 feet per second. For our instantaneous velocity, we're going to want to pull out our limit definition for derivative again. So we get our p of t plus h minus p of t, and then what we're going to do at the end is just put in t equals 5. Okay, so we'll go and expand everything out. So we'll go and pull out our limit definition. and find p prime of t equal to the limit as h goes to 0 of p of t plus h minus p of t all over h, and then at the end, after we found our derivative function, we'll go and put in t equals 5 to give us the instantaneous velocity. Okay, so we wind up with our p of t plus h minus our p of t, and then we'll go and start expanding things. So the first thing that we can see is that we'll have a plus 40 and a minus 40, so those will cancel away. Then we'll have a 96t, a 96h, and a minus 96t. So the plus 96t and the minus 96t cancel each other out. And then we'll expand the t plus h squared, so that'll give us a minus 16t squared. And then over here we have a plus 16t squared, so those two cancel out. And then everything that'll be left in the numerator will have an h in it, which is exactly what we want. So now we can factor an h out of everything in the numerator and cancel that h with the h sitting in the denominator to give us the limit as h goes to 0 of minus 32t minus 16h plus 96. That's a polynomial in h, so we can evaluate that polynomial at h equals 0 to give us minus 32t plus 96 for our derivative function. Because we want the instantaneous velocity at t equals 5, we'll go and evaluate that derivative function at t equals 5 to give us minus 64, and in this case again we're using units of feet and seconds for time. So for the physicists among us, our final answer would be the instantaneous velocity at 5 seconds is minus 64 feet per second. So with this, the minus sign just means that the stone is going in the downwards direction, where we're taking positive to be up and the negative direction is down. Right, so if we were to plot the path of the stone over time, it would look like this. So we're starting here at 40 feet, it goes up, and then it comes all the way back down, and what we see is the place where the stone's going to hit its apex is going to be where the slope of the tangent line is 0. So in other words, where the derivative function is 0. And from the plot, it looks like that's at 3 seconds. So let's go and show that. So we want to find where our derivative function is equal to 0. We can easily solve the derivative function equal to 0 and find that, yeah, it's equal to 0 at 3 seconds, which is exactly what we thought from the plot. So to find the maximum height of the stone, we just need to evaluate our position function at 3 seconds. And when we do that, we wind up with 184, and again, for the physicists among us, that would be 184 feet. Okay, so that I think wraps up everything we need for the basics for derivatives. So again, tomorrow I'll go and do a video over a computer algebra package. So it gives you another tool maybe for checking homework and things. And it's also useful for other math courses that you might do. So if you're taking linear algebra, or you're going on to Calc 2 or something like that, you know, it's good to have an idea about some computer algebra packages. It definitely helps. Then Thursday, I'll leave open a Zoom call for anyone who has questions about the test, and then we'll have our test on Friday. Okay, and I will see you all then.